Welcome back to Bewitching Brain. My name is Sophia Mazacchio, and I'm an MD candidate at the Medical College of Wisconsin. I'm super interested in the brain and nervous system as a whole. At the Medical College of Wisconsin, the Student Interest Group in Neurology provides educational outreach and is always looking for ways to engage community as we learn more about the bewitching brain. Please subscribe, share, and email me, or comment below with ideas or questions. Take good care, be safe, and help others be safe. This week we will be discussing the action potential. Okay, so here's a slide we discussed a few videos ago. We reviewed the parts of a neuron and introduced the synapse. The next couple of videos will be all about signaling within and between neurons. There are two basic components to this signaling process. First, there is the electrical signaling, which involves the action potential. Second, there are neurotransmitters, which take the electrical signal and send it as a chemical signal through the synapse to the next neuron. Today's video will focus on the action potential, while our next video will focus on neurotransmitters and the process by which the electrical signal is converted to a chemical signal. So, what is the action potential? It is an electrical signal that is spread in one direction down the axon of a neuron all the way to the axon terminal. The action potential does not change as it spreads. You might think of it as a car heading down a one-way street. The car is on cruise control, so it does not change speed, nor does it reverse direction. Once it gets to the end of the street, it stops. Another important point about the action potential is that it involves membrane depolarization. In other words, the membrane becomes highly positive during an action potential. As you may have guessed from the previous slide, graded potentials can be summed. This is a distinct property from action potentials, which are all or nothing. Also different than action potentials, graded potentials can go in different directions. Think of graded potentials as go-karts moving around in a circular arena. So now that we understand the basics of signal transmission, let's get into the nitty-gritty of how an action potential actually works. First, graded potentials created by sodium influx in response to neurotransmitter binding will sum to create a small membrane depolarization. Once the membrane reaches a certain threshold of depolarization, voltage-gated sodium channels will open. When voltage-gated sodium channels open, sodium flows down its concentration gradient into the neuron, and the membrane potential becomes even more depolarized. Let's explore this again on the graph. You can see that on the very left of the graph, the membrane potential is at negative 70 millivolts. This is the resting membrane potential of an average neuron. Then, the membrane becomes depolarized to some threshold, say to negative 50 millivolts, because of graded potentials. Once this threshold is reached, the depolarization triggers voltage-gated sodium channels to open, and the membrane potential rises as a curve and peaks around 20 millivolts. When the membrane is highly depolarized, This triggers voltage-gated potassium channels to open. Because potassium is at a higher concentration inside the cell, potassium will flow outwards, making the membrane potential more negative. You can see this in the downward slope of the graph on the right. There's a delay in the closing of voltage-gated potassium channels. This causes the membrane potential to go below resting membrane potential. This is called an overshoot. You can see this on the far right. The membrane potential then normalizes to resting membrane potential. This entire process can take anywhere from around 10 to 100 milliseconds. Let's review that process by looking at those changes on a molecular level. On the left, you can see the graded potentials creating a small membrane depolarization. Then, the first voltage-gated sodium channel opens. This allows positive charge to flow in, triggering opening of the next voltage-gated sodium channel, and so on. The action potential only travels in one direction because sodium channels inactivate after opening and letting sodium through. We won't get into the details of inactivated versus closed here. But you can see that this mechanism results in propagation of the action potential down the length of the axon to the right, all the way to the axon terminal. Again, the opening of voltage-gated potassium channels, once the membrane is depolarized, allows the membrane to repolarize to resting membrane potential. Next time we will discuss what happens when the action potential reaches the axon terminal. Thanks for listening, Brainiacs. Tune in next week for more.